Originally, we had big balls of mud. They were created due to poor design thinking. And then microservices, the salvation came around, and the same poor design thinking was applied. Just instead of creating one component, people created a distributed system. The problem was never about the lack of distributed components. The problem was in the design. We just elevated those problems on a higher level of abstraction, and now it made it much harder to fix those design mistakes.
Okay, hello everyone. So I'm here today with Vlad. So I'm really excited for this episode today. Just to let you know, this is the first Dev Lab cast in English. So it's part of the new season of the podcast where I talk to like authors and people that I like that are not part of the Brazilian community, but I want to bring these people, I think, closer to our community because there's such a contribution that you guys do to us. And just to introduce you guys, Vlad is a software architect, a keynote speaker and author. He's an author of like learning domain-driven design and balancing coupling in software design. And I invited you here mostly because of the second book, Balancing Coupling in Software Design, which is almost my Bible now. I talk about this book to everyone. But before we start, Vlad, can you introduce yourself, talk a little bit about you, and yeah.
Thank you so much, Valdemar. Thank you so much for inviting me. It's a pleasure being here, talking to you. And yeah, I love software. Been programming for way too many years now. Always been trying to find better ways to do it. And that book that you mentioned, Balancing Coupling and Software Design, first of all, it's the hardest project I ever worked on. And second, I treat it as if I put my soul into that book because everything I know about software design is there. I love domain driven design, for example, but I kind of extracted, the distilled principles of domain-driven design, and it's there in the book about coupling. And yeah, uh, I guess your introduction already mentioned that I'm a software architect, and yeah, I love building software, and
Nice,
I
that's
hate
great.
writing books.
I like I told you that I'm writing a book about like modular architectures, right? And I have a book about Node.js, like applications with Node.js, which is one of the most downloaded books in Brazil. And I promised myself I'll never write a book again. And now I'm writing one again. So like it's such a hard thing to do, like because you think you have all the things in your mind, and then you start writing, and then you get stuck at some point, and then you have all the ups and downs, right? But that's a topic for another podcast. So how I got to know you. I got to know your book while I was developing my course about evolutionary architectures. I have been like researching this topic for quite some time, and I saw mostly that I saw that mostly like big techs, they were struggling with granularity, mostly about like microservices and stuff. And like the small companies, they have no guidance about how to evolve systems from monolith to microservices as well. Then right when I was starting working on the module communication part of the course, like about how to design modular systems and how to have low coupling between like these modules, I found your book, and man, that was super helpful because it it brought a lot of things in a very clear and structured way that they were in my mind because of my experience. I think we, like you have a lot of experience. Like there are things that we just know when we are designing a system, but when someone brings that in a very clear way and explains to you like this is like coupling, like that, I want to talk to you about the dimensions of coupling as well, which is something that I use a lot, like the strength, the space and time, all those things, like they made so much sense, and then you reached my content so much. So you were like part of my course that you don't even know, but like I remember, like I read the book and I was like, this will help me a lot to explain to people what I want to say. But I want to hear from you. What was your motivation to write a book about like coupling, right, and modularization?
Yeah, it all starts with my love and hate relationship with microservices. I hate microservices because so many companies found themselves in troubles because of the microservices hype. I was one of them. But on the other hand, I love microservices because it gave so many opportunities. For me as a DDD practitioner and for me as a software designer, because now suddenly found so many case studies to investigate and to understand what was wrong there. And out of those experiences came out this idea of, maybe we should start thinking about coupling as a tool for designing boundaries of modules and microservices. And actually, it came from a book that was published in 1976, if I remember correctly. And of course, it doesn't mention microservices or anything like that. It talks about programming in COBOL, Fortran, and other fun languages like that. But the problems that the author addresses in the book, they are so similar to what we are facing nowadays. And I found the solution of why that project that was based on the microservices architecture failed. And the answer was in the chapter on coupling. And since then, I started learning whatever I can find about this topic of coupling. And I discovered that we have a pretty large body of knowledge about that. But unfortunately, it has been forgotten many years ago. It's like we figured that out, but we forgot it as an industry or as a field. And what I did was I adapted all that, let's call it forgotten knowledge, to our modern day software engineering world. The tools that we are using nowadays, the problems we are facing nowadays. And I tried, to lower the cognitive load on a person that's just getting themselves into this topic, just learning about coupling. So, I try to avoid that person from having to learn terms in COBOL and Fortran, and instead
Yeah,
to
thanks for that.
to find a terminology that better conveys the ideas behind those terms. And that's how the balanced coupling framework came to be. And yeah, 4 years later, that book was finally published. And as I always say, that book is published 3 years after its original publishing date, which proves that I'm a real software engineer.
Nice, yeah. And it's funny, like you talk about microservices, like because it's same reason that I started researching about evolutionary architectures and stuff, and I kind of landed in the same conclusion as you, that modularization is one of the key patterns to like be able to evolve systems in a sustainable way. And what I found interesting about what you're saying is that you have been researching this like for, I don't know, like the book takes it took like 4 years, and you said like you have been researching it for 3 years before. It's like 7 years. So you realized this problem with microservices like way before the rest of the industry, I think, and then you start working on this book. And I think the book came at the right time, because now everyone is a bit like skeptical, at least, about like the cost of microservices and stuff. And I assume mostly because of the pandemic, where we started looking at efficiency and cost and stuff. And I think, yeah, it's a great great timing, by the way. um what I'd like to ask you, like, now I want to dig more into the technical details to help people like design systems. And can you explain what is a module in your like definition of a module?
Oh, so you are starting with hard questions. Yeah, that's one of those overloaded terms. So many people have different meanings for what a module is. And, you know, for me, I had to go way back into those days of late 60s, early 70s to see how that term was defined back in those days when the notion of modularity was just introduced to software. And I came to the realization that modularity as a concept is the opposite of complexity. Let's say that you have a code base that's complex. What does it mean? It means that, first of all, if you want to read it and understand how that system works, that cognitive load is beyond an average human's ability. So it's going to be impossible. Second, if you want to make a change in that system, if it's complex, well, you're going to make the change, and either you're going to be surprised by the outcome of that change, or you will have to do a few experiments to find out what the outcome is going to be in the future. That's what we usually define as complexity. Modularity is the opposite. If you have a modular system, then it's easier to understand how that system works. It's easier to understand what the core components of that system and how they're interacting. If you have to make a change, that change should not require experimentation. You should be able to understand what you need to change, and you should not be surprised by the effects of that change in the future. You know, and to achieve that, it all boils down to the boundaries of modules, boundaries of those components of that system. Now, if you take a system and divide it into an arbitrary set of components, we like just draw a boundary here and here because for some arbitrary reason, we just divide it into components without any design thinking about what we put on those boundaries. In that way, we are not going to get a modular system. What we'll get is probably that complex system. So to achieve modularity, we need to divide that system into components, into modules, in such a way that it will optimize the cognitive load on the person who will have to work in the future. Now, to define a module, we have to think about what's the difference between an arbitrary component of a system and a well-designed module. For me, a well-designed module is one that encapsulates the most knowledge within it, but yet provides a simple, easy to use interface to other components of that system. For me, that's a module. That's what I can describe in a few minutes without getting all the way into integration strength and distance and volatility on all that stuff.
No, I think it's a great I think it's a great definition about a module, and it reminds me. I'm not sure if you have read the a philosophy of software design, where the author talks about like shallow and deep modules, like more from a class perspective or
Mhm.
something like that. But he talks about the same thing, like a deep module is a module where everything that is important is encapsulated and it provides a very simple interface for people to use, right? And a shallow module is that module like there you receive a lot of parameters. There's lots of thing, like a lot of things happening, lot of side effects happening and stuff. So I like that, like overall, like you guys are aligned, like even though you talk more deeply about modularization, it's aligned with that concept that I like as well, of like providing simple interfaces and like try to like encapsulate everything that makes sense together, right? um so you talked a little bit about complexity, and you bring in the book the framework. I think it's Kunevin, right? The name, is that how I pronounce that? Yeah,
Yeah, it's Kinevins, like Kevin, and you sneeze
Kunevin.
in the middle.
Yeah. Yeah. I found that very, very interesting as well, because it talks about this the cognitive loads and unexpected things happening. And I think it's a great way to define complexity, is like when something that you don't expect happen, right? You change the database table, and then another thing gets paged because some of their services broke, right? Like you don't expect that. So that's not proper modularization. Modularization is not only in the code, is on the whole thing, from what I understand, including the database, including the whole infrastructure that you use, right? And you talk also, like the next question is like you also talk about like local and global complexity. Can you talk about that as well?
Yeah, so by the way, I picked up these terms from the same book that I already mentioned from 1976.
No.
It was defined in the same book called Composite Structure Design by
Is the
Glenn
author still
Myers.
alive?
Yes, Yes,
We
as
could
far as I know.
invite him for a for a podcast.
I tried reaching out to him, but he didn't respond. Yeah. So I'm using these terms because in my mind they help me to express design issues. Sometimes when you make improper coupling design, it's going to result in complexity of the component that you are working on. So that's going to be local complexity. You are working on a component, making a little mess there, so you are increasing its local complexity. If, let's say, you are making some little mess on the boundary of that component, something that is going to result in unexpected outcomes during the integration with this component, then you're actually increasing the global complexity of the system. The complexity is between your component and other components of that system. So it's a global one. And I started using these terms like for the first time I found like the real power in these terms when again talking about microservices, because back in the day people were complaining about monoliths. It's like we have this one system and it's complex. We don't understand what's going on there. Let's divide it. We're not going to introduce any design thinking into how we're going to define those modules, those microservices. We'll just extract something, put it in a executable, etc. And what they end up doing is they transformed local complexity into global complexity. So they went from a big ball of mud to a distributed big ball of mud.
Yeah, exactly. Yeah, yeah, that makes completely sense. And so continuing on that, why do you think like modularization is such a hot topic now? Because and I don't think it's a hot topic, but people are talking more about this, right? That I don't know. Myself and you, we came to the same conclusion about modularization in the different. Like when you were in Israel and I'm here in Brazil, like how did that happen? Like why is it like why we are paying more attention to modularization now, even though it's not new, right? You could like have like Java packages, even desktop apps in the past, right? So why do you think that?
Well, to be completely honest with you, I don't think we're paying enough attention, uh, especially nowadays. Now, if you look at the way that new concepts were introduced to software engineering field, like we have procedural programming, then object-oriented programming, then we had SOA, microservices, now we have cloud components, and all of them have that shared common denominator, and that's boundaries. We are introducing boundaries. Boundaries, whether doesn't matter what level of abstraction they belong to, whether it's high level abstractions like microservices or low level like objects within a microservice. All of them are boundaries. All of them encapsulate some of the knowledge. All of them allow some of the knowledge to flow across the boundaries, and that's modularity. It affects everything we do when designing software. Doesn't matter what is the level of abstraction. Now, today we have another reason, to think about modularity, and that's our new friend AI, because in my experience and in experience of other people that try that, if you're working on a large system and you want to maximize the the benefits you gain from using an AI, you better invest in modules, because if you have a module that has like well-defined boundary, AI will have much better chances of understanding what's going on with that within that module and making the necessary changes, compared to, let's say, you feed it the entire monolith and then it flows out of the context, or maybe you have a distributed monolith, so you're giving it a service, asking to do some changes. It is going to do those changes, but the effects of those changes are going to be discovered, well, if you're lucky when you deploy it. If you're less lucky, then maybe on the weekend after you deploy it.
Yeah, no, it makes sense, and that's another it's another area that I'm starting to research. is the impact of AI in architectures in general, and kind of coming to the same conclusion as you, like having the code together but modularized is a great way to let the AI work, right? Because if you have the code separated and you want to make a change that maybe impact multiple modules, it's hard for the context of the AI, right? But if you have the code together and the code doesn't have any modularization, the AI will just like the blast radius will be enormous, right? Because it starts like updating a lot of stuff. But if you have a proper modularization there with clear boundaries, the AI will understand like, okay, this module only exposes this part here. This is the way that they can talk to this module. And I think it's great that you brought it. I took a note here for us to talk more about that in the future. But that's good. So I want to run you through my thesis about like modularization as well. It's like, so when microservices came in, like we were suffering with monoliths mostly because we were not properly designing monoliths, even though you like you know a lot about DDD, right? Even though DDD talks about like modularization bounded context since the beginning, I don't think we were designing systems thinking about modularizations in the past, right? So what happened was that a lot of like monoliths, old monoliths, they were just big balls of mud. And then when microservices appeared, even though microservices were created to solve scaling problems, people started migrating to microservices and then they started thinking about like bounded context and how to split stuff. And they saw that smaller code bases, right, like lower local complexity, is easier to maintain. It clearly requires less abstractions, right? It's much easier to maintain. It's more focused on one part of the domain, and that's why I think a lot of people start migrating to microservices to solve a complexity issue of the monoliths, right? But they solved the local complexity and then they created global complexity. And then a few years after, they need something else. They need a way to solve that. The way to solve that is the modularization in a monolithic code base or something like that, right? What do you think about my thesis? Am I looking at this right?
Yeah, absolutely. So originally we had big balls of mud. They were created due to poor design thinking. And then microservices, the salvation came around, and the same poor design thinking was applied. Just instead of creating one component, people created a distributed system. The problem was never about the lack of distributed components. The problem was in the design. We just elevated those problems on a higher level of abstraction, and now it made it much harder to fix those design mistakes. And yeah, as you mentioned, we just converted local complexity into a global one. And global complexity, well, it bites back. It bites back fast. The moment you need to change something, yeah. The first version is awesome. If you're a consultant, if you are an outsourcing company, you deliver that first version, and then you never answer any calls from the same customer. You tell them that you have other gigs to work on.
And the problem is that it's cool to develop, right? You feel that you are doing something great, like you are setting up infrastructure to run multiple services, and then you have that services talking to each other, and you think like, I'm a software architect here, right? So because usually the sustainable way to build software is kind of boring, right? You kind of like develop things together. You think about the boundaries. You keep like upgrading those boundaries over time. But when you look at the microservice, it's exciting, right? Like you create that big infrastructure, like a lot of things talking to each other. But the problem, as you said, it bites back, right? And then you have
Yeah,
nightmares.
yeah, yeah. Well, I don't know if it's boring or not, um, but look, some I always advise people to start with wider boundaries, wider boundaries of bounded context of their services, etc., and then make them smaller as uncertainty decreases over time, as you have more confidence in your knowledge of that business domain. Now, that period of time is not boring. When you have so much uncertainty that you have to verify all the assumptions you're making that you are basing your design decisions on. Well, that's not boring because you have to be sure, not to miss any invalidated assumptions. Because if you do, that's big ball of mud starting to roll.
Exactly. Now, when I say boring about technology, because you
I
won't be
see.
using, like, you won't reinventing the wheel or something. You'll be using probably your language of choice, right? Your database of choice, and you can go very far with that, right? And then you keep designing on top of that, right? You don't need like a lot of infrastructure around that. So that's what I was saying. But yeah, I agree with you. So so my next question is like, how to balance like coupling in software design? How do you evaluate this, and how what are the things that people should look for to identify like coupling?
Yeah. So the thing about coupling is that we kind of used to treat it as something one dimensional and something binary, that it's bad. Cohesion is good, coupling is bad, and that's it. Um, if you look into some of those earlier books from 70s 80s, you will find some models that were used to evaluate coupling in more of one dimensional way. It's like we have different levels of coupling, and the higher level is bad, the lower level is good. That's the way you refactor your code base. Good luck with your endeavor. Uh, just to make sure I got my message across, that's how people treat it. That's not what authors uh, meant when they wrote those books. So what I discovered is that coupling is a bit more complicated. It is multidimensional, and you can observe those dimensions when you really pay attention to what people mean when they say that two things are coupled. First of all, let's say that we're talking about that scenario of a monolith being decomposed into microservices, being refactored into microservices. Why? Well, usually people tell you because everything is coupled nowadays. We cannot change one component without redeploying the rest of the system. So here what they mean is that we have life cycle coupling between the components. They share the same life cycle, right? If you talk to people from upside, they will tell you, well, right now in this monolith, everything is coupled because if this thing fails, the whole system fails. So we have that runtime dependency. If you ask engineers, they will tell you, hey, of course it is coupled because if something changes here, we have to make corresponding changes here, here, and there. It is coupled. Now, those are different things. Those are different manifestations of coupling. And we can bring a bit of order into that by identifying three distinct dimensions of coupling. First one is knowledge. Let's assume we have two components that are integrated with each other. They have to work with each other. They cannot be independent. As people were saying 10 years ago, microservices are completely independent. You cannot build a system out of independent components. They have to be dependent in one way or another. They have to communicate. In order to communicate, they have to share some knowledge. That knowledge can be in form of integration contracts, like here's my API, here's what you can do. Those integration contracts can share some information about the models of the business domain that are being used internally in the component. For example, if that model has to change, if that change will necessarily require corresponding changes across the boundary of the component, well, the knowledge of the model is being shared. Then we have the knowledge of functional requirements. When you have multiple components implementing closely related business functionalities. The effect of that is that if there is a change in the business requirements, it is necessarily going to require multiple components to change together. If only one of them changes, then the system will end up in an incorrect state because probably they will come up to different uh, conclusions. The same input will produce different outputs, for example. And finally, We can share knowledge of implementation details. Microservices, let's say we have two microservices, we all know that they should be integrated across their public APIs, but we decide that we know better, we have access to the database directly, we'll pick up something from there. While we are there, we'll also change something because why not? That's wrong, we'll know better. Well, that's dependency on implementation details. Something changes in those implementation details, a corresponding change is required in whoever has that knowledge as well. So that is one aspect of a coupling. We have knowledge that is being shared across boundaries of components. What I just outlined is the model that I call integration strength. It defines four basic types of knowledge that can be shared across boundaries of components, and it also has degrees, like how do you compare integrations of the same type, like some of them may share more knowledge than others, etc. But fundamentally we have four types of knowledge. Why it's important for us? Well, the more knowledge we are sharing across the boundary, the more cascading changes will follow. We have higher likelihood that something will change and that knowledge that is being changed is reflected in some other component in the system. In other components we are coupled to. Well, guess what? Now you have to change them as well. And the more such components we have, the closer we are to that big ball of mud scenario. So that is one aspect of coupling. The second one is related to what we talked about earlier, like lifecycle or runtime dependencies. And let's say we have two components that are coupled to each other. They share some knowledge, but where are those components implemented? Where is their source code? They can reside, let's say, in the same executable, maybe in the same package, maybe in the same namespace, etc., however you want to call it. Or they can reside in different services. In the first case, the source code is close to each other. In the second case, it's far apart. Well, if you are going to change the two components that are coupled and you need to change them simultaneously, the larger that distance is, the more painful that change is going to be, the more effort you will need to invest into communication and coordination. Now, on the other hand, the closer those components are, on the one hand, yes, it will be much easier to co-evolve them, to change them simultaneously. It's like changing one component. They're close to each other, maybe even in the same file or in the same folder, the same repository, etc. On the other hand, the closer they are, the more coupled is their life cycle. They share the same life cycle. They have to be deployed and tested and implemented simultaneously because they're close to each other. So we have that balancing thing between distance as cost of change and life cycle coupling. Now, overall, we have two dimensions. We have knowledge sharing and we have distance. Let's say that we have two components and we want to design a modular system, so we'll try to minimize that shared knowledge as much as possible. It's not always possible to minimize it. Sometimes you do have to share knowledge about functional requirements or the model of the business domain. So you'll have to identify that possible minimal level of knowledge that you have to share according to your business requirements. You refactor your code base accordingly. Now, the question is how do you balance the distance? Let's say that you end up with that perfect scenario where you minimized the knowledge that is being shared. In that case, well, if you're going to put those two components together in the same, let's say, folder or the same namespace, the same package, well, they're not sharing much knowledge. They're not going to co-evolve together. Uh, if there are only two such components that are not really related in the same location, that's not a big deal. However, if you have like tens or hundreds of such unrelated components, what you're creating is cognitive load when you will have to evolve that component in the future. You are increasing the local complexity of your component. So it's going to be beneficial to increase the distance between them. So once you minimize the knowledge, you can increase the distance. And then you're achieving what we usually call loose coupling. We're minimizing the knowledge, we're minimizing the likelihood of cascading changes, and at the same time, we're increasing the distance to reduce the life cycle coupling between them. And we have the opposite scenario. Let's say that you ended up with a considerable amount of knowledge being shared. Maybe you need to share functional requirements because that's the nature of business domain. In that case, if you put them far apart across a bigger distance, well, guess what? They will change together, and each change will be expensive and there will be pain in your future. So instead, you better put them close to each other. You better minimize the distance. So we have that other relationship of high amount of knowledge or a high level of integration strength and lower distance. And that's what we usually call high cohesion. We identified components that will change together. So we are optimizing for those changes in the future by co-locating them in the same component. So that's the basic, the core idea of the balancing coupling formula. We have those two dimensions. The third one is the dimension of volatility. And this one is about the nature of that business domain. Will those components really change in the future? Because if they are not going to change, maybe because they belong to a legacy system that is not going to be evolved, or maybe they belong to a type of business functionality that the business doesn't really care about. Like there is no competitive advantage there, so it's not going to be evolved that much in the future. In that case, sometimes it's okay to round corners here. If you identify low volatility, then it's okay to introduce some complexity and to be a bit more pragmatic because, well, you are going to focus your design efforts where it matters most, where the volatility is high. If volatility is high, well, in those areas you have to make sure to balance the knowledge and the distance it is going through. So that's the idea of balance coupling: three dimensions and those relationships between.
So you were talking about like the dimensions of coupling, and I think it reminds me so much about like domain driven design and how important domain driven design is to be able to get it right. So many things that you talk about starting with wider modules, which I think is fundamental. And like part of my content, I talk a lot about that because nowadays there is a lot of people doing like vertical slices or feature slices that are super granular and share a lot of like domain logic, which makes in the end not very granular because they are coupled. And like starting with wider modules and then start breaking them like when the necessity comes is such an important thing. And to be able to get it right, you have to design it properly, like following like domain driven design and stuff. And then you talked about volatility as well, which is also like related to like probably your core domain is the thing that changes a lot, and the other things are not like that important. And that's a good way to look into that, right? So I wanted to ask you, like, you have a lot of experience with domain driven design. How do you see domain driven design like mapped like to software nowadays? What changed and what is the important part?
Yeah, so domain-driven design, it was introduced quite some time ago. That original blue book is allowed to buy alcohol in all 50 states of United States of America right now. It's 21 years old. So I guess that time, that age proved that methodology is still relevant because, come on, it has a very good track record. So it's very important. Now, if only we could teach everyone domain-driven design, the world of software engineering would be, in my opinion, a much better place. But it's problematic, unfortunately, and there are many struggles that I hear from people that are learning domain-driven design. and trying to introduce it in their day-to-day work. That's why, by the way, in learning domain-driven design, I talked about how you can introduce that methodology gradually into an organization. Don't expect to do all or nothing. Start gradually then picking some stuff, see that they catching up, and then introducing others, etc. In the coupling model, I tried, to extract that essence of how domain-driven design helps you with identifying good boundaries and just provide a different way of expressing them. That's, by the way, the notion of volatility. It came from domain-driven design. Supporting subdomains. They're not going to change. Volatility is low. That's why Eric Evans famously said that not all over a large system is going to be well designed. Well, because you have those parts where you can round some corners. And so, yeah, in my opinion, domain-driven design is not only is relevant, but it's going to be even more relevant because the core idea of domain-driven design is ubiquitous language. If you ask me what's like the most important part of domain-driven design, it's not aggregates, not the tactical part, it's the ubiquitous language and the thing that you need to sorry, to foster ubiquitous language, the bounded context pattern. Those two things, they're the most important concepts of domain-driven design. Now, speaking of ubiquitous language and our brave new world of vibe coding, what do you use to interact with AI? You use a language. So I think nowadays it's even more important to make sure you have a well crafted model expressed as a language that describes your business domain. So yeah, in my opinion, domain driven design is as relevant as it ever has been, just as modularity.
Yeah, no, that makes complete sense. And I remember like reading your book. I could I could see a lot, and I like it that you tried not to bring too many like concepts from other books into that book, like to make it simpler for people to read. I think like you didn't go too much into the domain driven design and stuff, even though you can see that a lot of concepts are like inherited from domain driven design, and I like that. And I like that you talked about like the ubiquitous language in more like a strategic part of domain driven design, which is I think is something that we can use like in any project. But what do you think about the technical part? I think the technical part is something that kind of evolved a lot from the like the I think from the beginning, like a few years ago, when you talk like 20 years ago, we were trying to abstract like big like monolith code base and try to map that in some way. And now with modularization, I see that like the technical part of DDD is is mostly around like the right level of modularization, the right times, and some parts, of course, if you have an e-commerce, maybe the purchasing part will have like aggregates, and other modules won't have it, right? But how do you see the technical part of DDD nowadays? Did it change in any way?
Well, my opinion hasn't really changed since last 10 years. 9 years ago, I wrote a blog post about domain-driven design and said that, in my opinion, the strategic part of DDD is the most important one. The tactical part of DDD can be uh, extracted and to allow us to have more options to make technical design decisions. During those years, I've seen a couple of projects, quite a few. Some of them, followed the strategic part of DDD and didn't follow the technical part at all. Those were code bases that I would call modular. They were well designed. I've seen also vice versa, people trying to implement technical patterns without thinking strategically about those components, about those modules, etc. Well, guess what? They needed help refactoring that mess. So, in my opinion, a strategic aspect is a must-have. Now, if you do the strategic part of DDD, then you can do the technical part of DDD as well. That's like an added bonus. It will work. You can also say, okay, I understand the why. I understand why the aggregate pattern was introduced, why those rules were introduced, what they are protecting me from, what are the principles. And once you understand that, you don't really need aggregates. There are other ways to implement that. Again, if strategically you think about modules and models, you'll be in a great place. And yeah, even without tactical patterns. Myself, I prefer, to do it the old-fashioned way. I love aggregates. I love to keep my transactional boundaries tidy. So yeah, that's my choice.
Nice, nice. It makes sense. And evolving more, like I wanted to ask you more about the impact of modularization in their different architecture styles. Like maybe starting from like a layered architecture. Like let's think about maybe hexagonal or a clean architecture. How do you see that the impact of modularization, this kind of architectures? How do if they work together or not, and how the thing of I'm asking more about like you talk about distance, right? So the more you abstract, in my opinion, the more you abstract things, they are far apart, right? Like you can have a little repository there behind an interface, and then you have your like core part of application here. So how do you see that the evolution of this layered architecture with modularization? Well, how do you structure applications nowadays? That's a
Mhm.
question.
Yeah, as many of us, I started with layered architecture, the classic layers, and notice that whenever we change something, that change requires changing the presentation layer, the business logic layer, the data access layer, and then the service layer in the middle if there is one. My preference nowadays is hexagonal architecture or ports and adapters, because in my opinion, it kind of fosters better modularity. It helps you with that encapsulation of encapsulating the core principles of your business domain and taking all the stuff, all the external stuff outside of it so that it doesn't pollute your model. Um, is it always necessary? Well, it depends. It depends on that volatility dimension, what you're working on. If you're working on a core domain, yes, that's important. Or maybe you're still working on a core domain, but what you're doing right now is sort of an experiment. You're experimenting with a way of formulating that core domain. In that case, it's okay to round some corners, and because you know that let's call it proof of concept is going to be a proof of concept no matter what. And yeah, I mean it seriously, because usually when people say yeah, that's just proof of concept, and then you see it deployed to production 10 years later.
So many proof of concepts in production, right? Yeah, yeah.
Yeah.
No, but that's kind of what I have been following as well. I think like what I like about hexagonal architecture that it provides a good balance like between abstraction and actually like simplicity. And because with like good modularization, you have less local complexity, right? And the like cognitive load and stuff. It's much easier into a smaller module, right? So you don't need to abstract too much. Like it's mostly like protecting yourself from external stuff and have a code base that is easier to understand. Because from my opinion, like when you open a module that says, I don't know, orders something, you want to see what that module does, right? You don't like need a lot of structure actually. You want to see, okay, this is what this module does, this is where the services are and stuff. And then hexagonal architecture brings you like that part of, okay, I want to protect myself from this stuff here, and I'm good. And I think that's a good balance. And I also think something that I have been thinking a lot as well is how, like, one thing that I have been working is the design of the modularization, like global modularization. Like say you have a modular code base, modular monoliths or modular architecture in general. You have domain modules, right? Usually are modules that are related to domain specific stuff. and you have infrastructure modules like logging, monitoring, and this kind of stuff. That in the end, you kind of have an hexagonal architecture in the global architecture, because you have that part that is your domain, and the other part is the like more infrastructure part, which is kind of similar. So I was thinking about that. In the end, we kind of copy some kind of structures and adapt them to the new needs, right? So you have inside the module and outside of the module, like globally, you also have that. So that's something that I was thinking a lot about. So next question to you: monoliths and modular monoliths. What is your opinion about them?
My opinion is my personal preference is modular monoliths because it's simpler, to change them, simpler to evolve them, and a design mistake in the boundaries is not going to be that dangerous. It's much easier to fix. It's much safer being wrong in a modular monolith. I prefer to start with a modular monolith, with a minimal number of bounded contexts that I need according to the organizational structure, and then, as I mentioned earlier, as uncertainty reduces over time, well, then we can talk about extracting microservices out of that modular monolith if there is a good reason to do that. Maybe we want to introduce new teams, maybe we want to reduce lifecycle dependencies, maybe we want to reduce runtime dependencies. Who knows? If there are reasons, we can do it, but I prefer to do it as the uncertainty about the business domain is minimized. Because again, we will be wrong. When working on core domains, well, we will be wrong. Our models are not going to be perfect on the first attempt. We will have to fix those mistakes. So at least let's make design our architecture in such a way that will make fixing those mistakes as easy as possible.
Yeah, like be able to delay as much as possible the decision to split the code base is usually great. So I see so many options that we have nowadays, mostly because of the tooling and instrumentation that we have. So nowadays it's so much easier to develop in a monolithic way and then deploy it separated, right? Even if you have like multiple teams, a trend that I have been observing now is the monorepo trend. Like I think Uber is a monorepo, like Meta as well, because when you go to microservices or shared services in different code bases, it's so much hard to have shared stuff and have like auditability and not like the setup of infrastructure for other repos. Have you thought about like monorepos? Have you looked into that? How they align with this idea of modularity and modular monoliths?
Yeah, to be honest, I've heard some things about people working in that kind of environment with monorepos, but personally, I never had a chance to work on one. So my opinions here are, you know, theoretical and speculative, and yeah, I prefer to stick to topics that I have experience in.
I'll send you my book once I do that. I'm working on that.
Deal.
That's my research. Yeah. Okay. So then you talk about a little bit about microservice, and okay, last one about services. Do you prefer going from a monolithic code base is, is straight to microservices, or do you like maybe having like domain services that are slightly bigger, that have like more modules into it instead of like going to like more granular microservices? What do you prefer?
Yeah, so my strategy is not really about intermediate steps, but more about the whole strategy. I prefer to start with logical boundaries to align the components of that monolith as if they are microservice and treat them as real physical boundaries, which means no references in memory, only through APIs, etc. Use that as learning experience, understand over time are those boundaries effective or not, then realign them. Again, logical boundaries within the monolith, they're much easier to play with. Over time, once you have more confidence, at that point, I don't really care if you're going to extract microservices or you're going to split that monolith in two and three. It doesn't matter. You have boundaries that you are confident about. You have tested them and they prove themselves. So yeah, I would say that's my preference. That's my focus.
Nice, nice. It makes sense. It's kind of aligned. I think I talked with you a little bit about the principles for modular architecture that I'm working on, and the first one is well-defined boundaries, which I think is fundamental, right?
Mhm.
So like you define boundaries, you don't let like internal things like be exposed. Another one is composability as well, like be able to compose modules, like run them together or separated. I think it's nice. Independence, they should not depend on each other. I won't talk about all of them, but explicit communication is like or APIs or events. When you talked about like the distance of the modules, I was thinking about that when you have modules or microservices or whatever that they are owned by the same team, it's sometimes okay to start with like a REST call, for example, between those modules. Like it will be fine because the same teams they own that, right? But if they are like spread far apart, teams in different organizations, the more tight coupled they are, the harder it is, right? Like that's usually a good moment to look to like I don't know, an event-driven communication or something like that that has some shared contract somewhere, right? What do you think about that? Is that a good way to look into it?
Yeah, so basically, what you're describing is switching from synchronous integration to asynchronous one. When you're doing that, the practical implication is that you're reducing lifecycle coupling even further. Now you have two components that one can be down, the other one will keep working. So you're reducing those lifecycle dependencies even further. That means that you're kind of virtually increasing the distance between them. Well, once you have an increased distance, you have to make sure that the knowledge is balanced, that it is minimized. Because if you have knowledge that is spilling across the boundaries, even knowledge of the business models that are being used internally, well, it is going to be it can be challenging to introduce such changes even if you have a event-driven integration, because if the change modifies the schema of this message as well, guess what? It's going to be fun.
Cool. So last question. So we have to talk about AI, right? Because there's no way we can record the podcast in 2005 without talking about AI. So you talked a little bit about something that I have been researching as well, like the impact of AI in the code base and the evolution of software. So how do you see AI? Like you talked about modularization that is important for AI to have boundaries. What else have you been using or looking into related to AI and yeah, code quality and evolution?
Uh, all I can say is based on my current knowledge, with a speculation about how the world is right now. If you would ask me the same question like 2 years ago, I would have never been able to predict
Yeah, no one,
the
I think. Yeah,
situation. Yeah. So,
yeah,
what's going to happen in a year or two? Well, who knows what's going to happen. Right now, my experience is we have high level design of components, of the boundaries of a system that is better be done by a meat and bones software engineer. Then once you have modular boundaries that are based on the knowledge of business domain and takes into account all the uncertainty about the domain knowledge in the company that is working on the system, then we have those safe boundaries and we can say, okay, AI, please implement the functionality of this module. And then we have that limited context, limited set of functionality. We have clear input and output, and it can work on that, without being aware of what happens in other modules in the system.
yeah.
That's my speculation according to the world as it is nowadays. Maybe, half a year there will be a new model that will be able to do modules way better than us. Then I don't know. Maybe
Yeah,
we'll do QA for AI.
yeah, maybe it can happen. But I think I think you talked a lot about you talked about domain-driven design and ubiquitous language, and like that it helps a lot AI as well. And I think one thing that will happen is like we will start adding more context to the code bases, right? It's like adding RFCs, ADRs, and stuff, which will have a lot of like business language into that, and that will try to map to the code. So I think that's a great advice as well. Like try to have like the code reflecting the business will help a lot. I understand things that are outside of that context. Once, thank you very much. That was like, really great talking to you. It's a lot of great insights. So just to close, how people can find your book and find you? Can you just give us some information about that?
My book is on Amazon, both of them. Learning domain-driven design and balancing coupling. They're on Amazon. You can find it there. If you want to buy them from other shops, you can find links on. I put up a new website recently called coupling.dev. There you can find the core ideas of the coupling model, and of course the links to purchase the book are all over the place on that website. So coupling.dev.
Nice.
And you can find me
Nice.
on LinkedIn, on Twitter. Just copy my complicated last name and you will find me.
Yeah, I'll add here to the description. Okay, yeah. Thank you very much. Thank you very much for taking the time to bring all this knowledge here. This is very helpful. And yeah, hope to see you soon.
Thank you so much, Valdemar.